In this video, we're going to discuss the ideal gas law and utilizing it to solve gas problems. So let's assume that we had a balloon. We'll call it a weather balloon. Definitely not an alien spacecraft. This weather balloon is way up in the atmosphere, and we're going to find that it is 297 liters in size. It's at minus 30 degrees Celsius. And way back down on Earth, when it originally came up, way down on the surface, when it had been down here starting, it was 138 liters in size. It was 25 degrees Celsius that day. It was 1.0 atmospheres. What we want to know is what was the outside pressure up at its height before it ruptured. Because at this height, eventually what happens to all weather balloons is they break open, the gas all escapes, and they fall back down to Earth. And so it was this size, this is its maximum expansion before it breaks. And so what was that outside pressure where it finally broke? Well, how would we go about knowing this? Well, we got to think, I have a volume, I have a temperature, and so there's volume and there's temperature, I know those. But I'm trying to find pressure. That's the thing I want. There's a way to relate these. If I have pressure and volume equals nRT, well, I know my volume, I know my temperature, I want my pressure. R is constant, so we can look up from our list which R to use for the units we want. We're in atmospheres, so probably the R for atmospheres of 0.08206 atmospheres, liters, mole, and Kelvin. So we know R. What I need is moles. If I knew how many moles of gas was in that balloon, I could solve the pressure. Well, how do I get moles? There's no info in the final to talk about it. But with a balloon, unless you have a hole in it, the gas isn't escaping, at least not at a reasonable rate. So whatever moles I started with are probably how many moles I ended with. So the question then becomes, can I solve the moles I started with? Well, I have a pressure, I have a volume, I want the moles. Again, we can pick our R, and yeah, we have a temp. I have the other unknowns. I can solve the initial moles that was in our weather balloon so that I know what the moles of it at the end were. I need to rearrange to do this. Well, if I want to get N on its own, I need to divide by RT on both sides. You make the same change to both sides of an equation, and it doesn't affect the equation. So R and T will cancel out. Pressure times volume divided by R divided by T will equal our moles. Pressure was 1.0 atmospheres. Our volume was 138 liters. Our R value is 0.08206. Atmosphere, liter, mole, and Kelvin. And our temperature, well, I need it in Kelvin. Our values always come in Kelvin. So 25 plus 273. 8, 9, and 2, 298 Kelvin. I can solve, and my original moles, which should still be there in the end for this problem, should come out at 5.643 mole of gas. So that should still be our moles at the end. And so I can plug in, rearrange for pressure. Well, my pressure should equal nRT divided by V. If I want to get pressure on its own, I need to move the V over. So I have to divide it on both sides. 5.643 mole. R value 0.08206 atmospheres, liters over mole, Kelvin, temp, minus 30 Celsius. Remember, I'm up in the atmosphere now. We're doing our later calculation. So negative 30 plus 273 for 243. 243 Kelvin. All over are 297 liters. So what is my pressure then final in the upper atmosphere? Well, we find that pressure has gone down to 0.379 atmospheres. So we got high enough up in the atmosphere to be down to, well, a little over a third of the pressure that's on the surface. That balloon got bigger. It also got colder. If it had stayed the same temp, it would have been even larger, but the upper atmosphere is colder, and so the reduced temperature would have tried to shrink the balloon, but the reduced outside pressure would have allowed your inside gas to push out farther, and so they kind of had competing factors. The temp wanted to make it smaller, the outside pressure wanted to make the balloon bigger. They factored each other out to 297 liters. By knowing the info at the start, we could find the moles at the start, which let us know the moles at the end, which let us find the pressure at the end. This is the advantage of the ideal gas law. As long as you know 3 of the 4 components of the gas equations, you can solve for the 4th. Well, let's explore a little bit. At one point, in terms of the pressure, our units are whatever unit we want. Atmospheres, torr, millimeters of mercury, there's many of them. Generally, we do volumes in liters just because, well, you need a reasonable amount of gas to do anything, and they're kind of spread out. If you don't at least have liters, you don't have very much gas. Moles, that's just what chemistry likes. We like moles, so it's kind of self-explanatory. But Kelvin, why do we need Kelvin? Well, one of the relations, if we think back, was temperature and volume. As our temp went up, our volume went up. But it also meant as the temp went down, the volume also went down. So if we think about temp and volume, you could experiment with the real gas and you could find its volume and its temperature and increase its temp a little and your volume went up a little. Increase its temp a little, your volume went up a little. In theory, this only works for so far, but you can actually project this trend line. You can say, hey, given this trend line, it's going to go down, and at some point, it's going to cross 0 volume. Now, no real gas can do this, because gas has physical volume, but you can follow the trend line to find where it would happen. Well, normally we tend to put like 0 degrees Celsius, 20 degrees Celsius when we make these plots. If I wanted to find this, I find it's minus 273.15 Kelvin. What does it mean to have 0 volume? Why do these gas laws obtain this for us? Well, remember, volume comes from motion. If I have a balloon and there's a particle inside hitting the walls, it's pushing the walls out. It makes the volume. As we slow it down, well, it can't hit as often, doesn't go as far, so the balloon gets smaller. And even if it's barely moving, I mean, if we zoom in and look at it falling between 2 walls, even if these are like 1 millimeter apart, that particle is still bouncing. It's still going to hit the walls, even if it's only moving a little bit. And if you got even more zoomed in, you got things where the atom took up most of the space, and you were nanometers apart, well, that particle still moves just the tiniest bit. And because it only has to go a nanometer, it's still going to hit those walls. How could you go to no volume? No motion. The only way to get 0 volume is if there's 0 motion, so there's no pushing those walls out. What happens here is that Kelvin tells us the absolute 0. You can't go colder than that because that's the point where you're not moving at all. And so this is part of where we actually calculated absolute zero from. By tracking back this linear trend line, we were able to figure out where the no motion temperature would be. Why this is so important is, well, if you double your volume, your pressure will be half. If you double the moles in a tank of gas, you'll double your pressure. If you double the moles in a balloon, you'll double your volume. They tend to be ratios of each other. This is true for temperature. If you double your temperature, you will double your pressure, or you will double your volume. But if we think about temperature for a second, if I have 10 degrees Celsius and I say double it, well, most people say times 2, 20 degrees Celsius. But if I said minus 10 degrees Celsius, double it, well, most of us think times 2 for negative 20 Celsius. That's colder. It doesn't work. Celsius, because it starts arbitrarily somewhere, it doesn't follow the ratios correctly. Going from 10 degrees Celsius, which is 283 Kelvin, up to 20 degrees Celsius, which is 293 Kelvin. In Celsius, it looks doubled, but in Kelvin, we realize it really went up like 5%. Kelvin is an absolute temperature scale, and we need that so that our ratios stay true for the ideal gas law and the other gas laws. So this is why we need Kelvin. It is part of the ideal gas law because it has to be an absolute scale of temperature. If my particles moving faster or moving slower determine how often they hit the walls, and therefore the force they apply and the pressure or the volume, then I need to know if they've decreased by half so they hit half as often or half as hard. And so we need an absolute temperature scale for our ideal gas law.